we have today's lecture, and tomorrow I am cancelling the class for various reasons. There won't be any class tomorrow. So we'll wrap up the course on Thursday with an extended class. It will be a 1.5 hour class, 12 to 1:30. So that will be the end of the course. There won't be any class after. So we have basically 3 classes roughly. And so I realized even if we had an additional 4, it will not be really possible to cover any topic in detail. So I'll give a rough survey of topics which we haven't been able to cover, and which with additional time I would have definitely liked to cover. So if you're thorough with what has been covered until last Thursday, you will be able to answer at least 90 to 95% of the course. But whatever I'm going to cover in the next 2-3 classes, if you just keep it in the background, there won't be any major questions, but you should it will help you in answering the topics covered so far. If you also keep in mind the various extensions and modifications that we are going to cover in the next 3 classes. So we'll first continue along the lines of what we have been covering last week, namely reaction equilibrium. We basically considered a single phase, how to handle single phase, single reaction. Now the most general case, so this the major new criterion was the criterion for chemical equilibrium, as it is called, and that is that the sum of the chemical potentials of all the species taking part in the reaction times the stoichiometric coefficient must have to add up to 0. And this was the basis for the rest of the stuff that we did, that you might even almost forget that this was the main criterion. Finally, we gave an expression for this in terms of the standard Gibbs free energy change of reaction, but the basis for, and the standard state and so on, definition of standard state. This is the basic criterion, and it's important to see how the criterion is generalized when you have multiple reactions and or multiple phases. So criterion is, we are not going to derive anything, but the criterion for multiple reactions, so when we have number of reactions taking place, one of the most important idea is to calculate the number of independent reactions. So certainly you might have encountered this in this idea in the mathematical methods course, whoever is taking it. Certainly you should have, even in process calculations in your BTech, you must have really heard of this idea, the number of independent reactions. Now there are different ways of approaching this. One is, if you're given a certain set of components, possible components in the, and then you're asked to construct the number of independent reactions. This you can do by constructing the so-called stoichiometric matrix, which will basically give, for instance, let's say we have possible, combination products. Let's say we have CO2, CO, and CO2, something like that. Right? So to say that oxidation or combustion of carbon, the products are carbon monoxide and carbon dioxide. So this is what we are given to us. Then we have to construct what is called as a stoichiometric matrix. So you put C and O, these are the elements. So what we need to really look at is look at the elements in the various compounds. And so I can put all the possible compounds and then construct the atomic coefficient matrix. So this would be 1, and for O2 of course it would be 0, and this would be 2, and so on. So we can then come up with the rank of this matrix will give the number of independent reactions possible. So that is one way of looking at it. Right? Another way is you are given a set of possible reactions, and then you have to check. So you have some idea, these are the reactions that are taking place, but you have to make sure that these reactions are independent, and if not, construct a set of independent reactions from them. So clearly see, the idea of independent reactions is, let us say I have 3 reactions, and the third reaction can be constructed, let's say, by just multiplying the first 2 reactions by certain coefficients and adding them, for instance. Okay? I wish I could give some examples offhand, but anyway, this is not the main thing that I wanted to talk about. So, if that is the case, then we have to construct the set of independent reactions from this. This is very important. So, when you have multiple reactions, whichever way you come up with the reactions, you have to make sure that the final set of reactions form a set of independent reactions. That means any one of the reactions, none of the reactions in the independences can be obtained from any other set, a reaction in the same set or any combination of reactions. So when you do that, the criterion will become something like this: sum over a very easy generalization for reactions I equal to 1 up to, let's say, R is the number of independent reactions. So the criterion for equilibrium will remain the same, but now I have to look at each reaction. So the I gives me the identity of the reaction, then it is the same. Here I am having only one reaction, so I don't need a subscript for that. But here I go to each reaction and then look at the number of components. Of course, not all the components may be present in all the reactions. This I am saying J equal to 1 to count the total number of components and then express this. But obviously, some of the stoichiometric coefficients will be 0 then, right, if some of the components are not present in the particular reaction. So we get a set of R equations. So if I have one equation, then I have one additional criterion. If I have R equations, then I have R different criterion, very similar to the single reaction. So that's all. We are not going to prove it, but it will be very much like when you look at each reaction separately and the sum of the chemical potentials of the species in that reaction multiplied by the corresponding stoichiometric coefficients in the reaction have to add up to 0. So that is a criterion. So it's a very simple generalization to take it from multiple reactions. Now what about the phase? It doesn't matter actually. Here we restricted ourselves to a single phase. We have multiple phases also. The criterion for chemical equilibrium remains the same. So it doesn't really matter. It could very well be that some of the components in a particular reaction could be in one phase, some could be in another phase. But it doesn't matter. The chemical potential of that component in that phase automatically would come in, right? So it doesn't matter whether which phase it is. We don't have to put a label, but it's very good to put a label. So we can maybe put a label like this, phi or phi j or something like that. So that because we need to know which phase a component is appearing, so that will determine what the chemical potential is dependent on. It will be dependent on the temperature and pressure and the mole fraction of the particular phase. Right? So it might be important to put that in so that you are aware that that component in that reaction is present in the phase, particular phase. Right? So we have our independent reaction. Now it is important to know what are the implications of the phase rule on the phase rule if you have reactions. Because the phase rule, if you recollect, the phase rule says the number of degrees of freedom is C minus pi plus 2. C is the number of components and pi is the number of phases, and 2 it's there. I mean 2 will come in. And so this is for no reactions. So there are no chemical reactions. This is when this is valid. So obviously when we derived this criterion, all we had was the equality of chemical potential of all the components in the various phases. right? And then we counted the number of those equations. The variables are obviously T, T, Z, the mole fraction vector in phase 1, 5. Now the common way the phase rule is arrived at for when you have reactions, when you have multiple reactions, those equations which we already had, so the number of variables remains the same. There are no new variables introduced just because you have reactions. So each phase is governed by the mole fraction vector of that phase. So no new variables, temperature and pressure remain, but we have now these new equations. The equality of chemical potentials continue to remain as constraints. They are not going to change, right? And then you have these R reactions. So the degree of freedom is given as like this. But if you see any reaction equilibrium problem really doesn't proceed or have any relation to the particular phase rule form that I have written. Most books derive this and then go on to solve problems in reaction equilibrium to make any reference to this phase rule or ever applying. And we just take an example for the single reaction, homogeneous phase. We took the example ammonia, so we saw that N2 plus 3H2. Let's apply the phase rule blindly. Now suppose consider the first case. I have this N2, H2 and NH3. No reaction is taking place, let's say. So I am considering conditions where I am not considering the possibility of reaction. Because we know that ammonia may not always form. In the negligible reaction, I will just say non-reaction. Now what are the degrees of freedom? It's a single phase, it's all in the gas phase. Right? So F is equal to 3 minus 1 plus 2, which is 3 actually. This is C plus 1, I mean 4, yeah. This is just C plus 1. Now what are the variables? T, P, Y, N2, if you want I can put Y, NH3. 4 variables. These are the independent variables, there are no constraints, there is a homogeneous mixture, no reaction. So we have F is equal to 4. These are the 4 variables. I can replace Y NH3 by Y H2, or I can have any combination of 2 mole fractions. So nothing is there to really, we don't have to appeal to the phase rule. We just know that if you have a C component mixture with just one phase homogeneous, the number of independent variables is C plus 1. And for a single component, it will be 2. We have already seen that. So there is nothing to even appeal to the phase rule. The phase rule depends on this. Phase rule depends on this assumption or postulate that for a C component in a homogeneous phase, C plus 1 variables are actually required to characterize that phase. Right? So now, however, if I allow for reaction, then the number of degrees of freedom will clearly reduce if I apply this equation, because there is no one reaction, and so this will be the equation. So the equation now I can easily write it, right? It would be 2 everything is in the gas phase, so I don't even have to mention the phase. This is the new equation that I have. Right? So this is one equation. Number of variables remains the same, 4. So the number of degrees of freedom now would be 3. Now the degrees of freedom are always chosen out of these variables, so it makes it appear that among the 4 variables, temperature, pressure and the 2 mole fractions, I can independently choose 3 of them. The other one is automatically determined. But if you look at the way we approach a typical reaction equilibrium composition calculation, we never really took any of the mole fractions as independent variables. And not only that, in the whole process of solving, we are actually introducing additional variables which are not there in the phase rule at all. Right? So what are these additional variables that we have to consider when we solve the equilibrium conversion problem? Must be having it in your notebook. You don't remember. Epsilon is there, then epsilon comes out as a definition. What is epsilon equal to? What are the other variables? Epsilon is not a variable by itself, it is defined in terms of what other variables. The mole numbers have to be introduced. As far as we know, for the phase rule, it is clearly we always deal with only intensive variables. Now the mole numbers are coming into play, right? Because we derive this criterion itself by bringing the mole number and the non-independence of the mole number into the picture, right? So if you look at the way we solve, what are the variables we introduced? We had temperature, pressure, and then we said N2 is N naught. This is the first variable that comes in. 1 minus x, right? And NH3 is NNH3 naught, another variable, right? So plus whatever, and NH2 is NH2 naught minus whatever. So now, actually what I have done is I have introduced, of course, when we calculate y, so we have now introduced 3 variables, new variables, and of course the conversion is also there. And if you recollect, of course we specify the ratios. If you are dealing with extent, then they directly deal with mole numbers. If we deal with conversion, we need to specify only the ratios. So if you see the way we did it, actually, in the calculation that we did, Tp, right? Yn2, of course, we also explicitly introduced Yh2, but that we know is simply 1 minus Yn2 minus Ynh3. Now, what is Yn2 a function of? Yn2 is a function of, or we can regard this as y, because I don't know whether you're getting each one. The y vector, it depends on the alpha, the beta, and the x, if you recall from this particular problem. So I am not dealing with mole fractions anymore directly. I don't go and specify the mole fraction. I only specify the initial conditions, initial mole numbers, right, and the ratio of the mole numbers. So actually the variables I am dealing with is not just 4, but Tp, 5 variables, right? So I am actually looking at 5 variables. So the common treatment of the phase rule doesn't really seem to match with what we actually did. Because the way we looked at vapor equilibrium or any other system without reaction was simply to focus on these variables. We never really looked at additional variables, but it seems like whenever we get into a reaction equilibrium calculation, we are not really looking at the mole numbers in themselves as independent variables which we can control, which obviously we cannot control. We don't control it that way, but rather we indirectly control it by specifying either the total mole numbers or the ratio. The point is that we can go to the ratios, we get only the ratios of the final the composition. We get only the ratios of the mole numbers. If I specify the mole numbers absolutely, then I will get the final mole numbers also of the reaction mixture. If I specify only the ratio, all I will get finally is also only the ratio. So we have 5 variables, and you can clearly see we specified 4, and then we use this equation to calculate the one variable which we didn't know. So the whole approach to the reaction equilibrium seems to be somewhat different in the way you approach the phase rule. Looks like we bring in more variables and then we specify some of them also. So it's not clearly following from this. Now if you rightly, there is still one degree of find this actually 4 degrees of freedom. If you look like there is just 4 variables, but if you look at it from the point of view of the mole fraction alone, degree of freedom is only 3. So it doesn't quite match with this, and so I think the whole approach to reaction to the phase rule has to be formulated taking into account this. So that's why I find a contradiction in the books. On the one hand, they deal with the phase rule independently in a very easy manner, because after all the variables are already there, phase equilibrium equations are already there, and we only have to introduce these mu r, and so this seems to follow quite well. But actually, it is never, when you go back and check all the standard textbooks, never used like this in any of the reaction equilibrium problems. So, we'll now take a few examples which deal with, for example, one of the standard examples I found, which deal with multiple phases. We'll go step by step. First, I'm not going to treat multiple reactions. I'm going to treat multiple phases and then how the phase equilibrium are to be combined with the reaction equilibrium. So, we'll take an example which I found in YBC Robert as well as Sand. Take that and look at how. What you will see is that the calculations are not really that more complicated just because you have an additional phase. So I will now take a single reaction, which is the decomposition of methane to give what is called as carbon black. So this is taking 2 phases, 1 reaction. Now, choice of standard state, now we will see how to choose different standard states for different components, which is convenient here. Now, the standard state that is chosen here is standard state 1 for this, standard state 2 for this, and standard state 1 for this. We are not making anything, clearly the only 2 components in the gas phase are methane and hydrogen. Right? We are not saying as yet that it will behave like an ideal gas-based state. That is not what it means when I say I am choosing an ideal gas standard state. But the standard state is open to choice. This is a very standard choice because we don't really choose the ideal gas standard state for carbon. Right? We will see why. Because first of all, if I want to calculate the delta G reaction, the question asked, that is the problem with YBC, is that T equal to 1 R and T equal to 1000 Kelvin. Find out the equilibrium conversion of methane to carbon black. The first step is to calculate the standard Gibbs free energy and the standard enthalpy change at 298 because that's what we would get. Now, at 298, if you take, first of all, hydrogen is not going to contribute because it is like an element, right, in its stable form at the given condition. So that would be 0. And carbon also, if you look at the tables, you won't find carbon. There are 2. There are different versions of carbon. For example, you see some books also give carbon within bracket they put diamond. For that, you will have a certain Gibbs free energy. But for carbon black, I think it's roughly taken to correspond to the regular carbon, and so it will have 0. So the only contribution is at 298.15. The standard pressure is 1 bar. So this is what we read out from the table. So the answer is minus, because the sorption coefficient is 1, so it will be minus of minus 15.66 kilojoule per mole, and so it's a high positive Gibbs free energy. So the equilibrium constant is going to be quite low. So the value Ka exponential of minus is, this is a 298.15, so it's going to be exponential of minus 50.66 times 10 to the 3 by 8 8.314 times 298.15. That is a very low number, 1.33 into 10 power minus 9. Now, if you calculate delta H reaction with these choices of standard state, is turning out to be again minus HCH4 IG at 298.151 bar, and that turns out to be 74 minus 74.943, and so this will be 74.943 kilojoules per mole. High endothermic reaction. So we expect clearly the Ka to be increased in temperature. A at 1000 Kelvin, if you calculate using the approximate formula, all these numbers you can easily verify. A at 1000 Kelvin. One approximation is Ka at 298.15, exponential of delta H by R, which is 74.943 into 10 cubed by 8.314 times 1 over 298.15 minus 1 over 1000 delta H by R, and 1 over T1 minus 1 over T2. So this will clearly be a huge positive quantity with the exponential. The answer we get here is 2.184. So a huge difference. These are all standard, very standard. And just want to point out that the calculation is going. This is a very simple case. And the actual case, there is quite a lot of beautiful values in the specific heat of the carbon, which you have to take into account to do the more general calculation. It turns out to be 7.91. Rather than 2, but this is big, you use factor of 3, more than a factor of 3 difference. If you neglect the temperature dependence of delta H, that you will be aware of. We've already seen it in the ammonia case. Right? Quite a bit of difference to be there. So you have to take that into account. And then now we come to the activity part. The Ka has been calculated. As I said, this is entirely choice of standard state, and 219 we can calculate 100,000 or any other temperature. We know how to extrapolate and calculate. Right? So that we have seen. So as far as the right hand side is concerned, there is no problem whether it's in the gas state or liquid state, or by proper choice we can calculate. And now we come to the activity part. So we have to now look at each component separately, because earlier we had a general formula where everything was in the same standard state. So that we have to now look at it carefully. So first of all, Ka is here. AH2 squared times AC divided by ACH4. Now for AH2 and ACH4, I have chosen the ideal gas standard state. So for them, AH2, if you recall the formula that we derived, is FH2 mixture. Right? This is all in mixture. Divided by the standard state pressure TSS. That is 1 bar of here. That's the formula. Same thing with ACH4. It's also FCH4. This is both of them are in the gas phase. Right? So carbon alone, in the solid phase, is a pure component. That's the advantage we have here. Also TSS. Now what about AC? You will see many books, whenever you are dealing with the solid, they will say take the activity to be 1. It is not as arbitrary, it is coming from the definition and choice of the standard state. So AC, right, we have chosen effectively standard state 2, that is a pure component state. So for that, this is Fc at the temperature and pressure of the mixture, of the reaction. It is a mixture of solid and gas, but the solid we have only carbon. Right? So it is a pure component effectively. It's a solid. Divided by, we saw that for that it is Fi of Tp, standard state. So this would be Fc of Tp standard state. So for numerator, if you recall for the standard state 2, right, it was Fj mixed, because we consider this part of the grade we are doing homogeneous mixture. So Fj mixed by Fj of Tpss. This is the pure component figure. If you recall what is T. So now we see that the carbon is there, but in the solid phase it is the pure component. Right? So that is the figurity of that under the actual reaction condition. That's what I have in the numerator. The denominator, I have the pure component. Here both are pure components because there is no other component in the solid phase. Right? So, but evaluated at the standard state pressure. That is the general formula. We can apply it here also. Right? So now if you see, for one thing here, V that you are asked to calculate is also 1 bar. So there is no contradiction in simply P is equal to PSS. So activity is clearly of the carbon doesn't contribute at all. So by proper choice of the standard state, you have actually got rid of the carbon which you might think is a problem because we have been dealing with gases so far. How do we deal with solid? Purely a choice of the standard state has become 1. But however, even if the pressure is 100 bar, it might still be justified to make it 1 because the pressure effect on the fugacity of the solid might be quite negligible. So that you have to take that into account. The 100 bar it might not vary that much, but it might be a good approximation. But here it's exactly 1 because the actual pressure is 1. If it is not, then I have to calculate this ratio. So I need to know how the fugacity is going to change with pressure for the solid, right? And that will of course depend on the volume, the density of the specific volume of the solid. The same formula applies here. So the mu, fugacity is just dependent on mu. So we have V. So the specific volume of the solid will come into picture, maybe by RT or something. We've seen how the logarithm of the fugacity of the formula d of F by dP is V times V divided by RT. Right? So we know that the specific the density of the solid is very high, specific point will be very low, but make a very minimal contribution. The pressure effects on the fugacity of the solid might be very negligible. So with this choice of standard state, even for a higher pressure, we might neglect the pressure effect and make it 1. So the whole calculation now stems on just dealing with the activity of the methane and the hydrogen. This is entirely the gas phase. 1 bar is a very good approximation to take it as an ideal gas mixture. Right? So we can simply replace this by P times YH2 mix. And this would be P times YCH4. The mix I want to put this really when we talk about mole fractions corresponding to the mixture. We don't take the carbon into account because this is entirely the gas mixture alone. So now we can construct it very easy. The reaction is given, right? So if I have for instance N naught, there is only methane that is being assumed. There is no hydrogen or carbon that is given, stated in the problem. So if I take NCH4 naught, so I can define a conversion which is given by this, and I need NH2 would be, as you know, hydrogen is present, it begins with, so it will be 2 times NCH2 NCH4 naught X. Right? So NCH4 naught minus X is the amount of methane that is reacted, right? So you will get this. So we can very easily construct the KY here. So P and PS are the same. So what I get here is that the KA, which I calculated to be 7.91, is going to be YH2 squared by YCH4. You can easily complete it. What you will get is you get 2x by 1 plus x. That's the total contribution coming from the total amount, and then this would be 1 minus x by 1 plus x is equal to this. So this will turn out to be very simple, 4x squared by 1 minus x squared, and x turns out to be 0.815. So very straightforward problem. So even if you're dealing with heterogeneous reactions, right, it's not that difficult. Right? Provided you choose the standard state appropriately, we just use the same set of equations. But now you see here, even though there are two phases, the phase equilibrium doesn't come into play. The phase equilibrium here doesn't come into play because the solid phase doesn't have any methane or hydrogen. We are negating any absorption of the gases into the solid. The solid also we are saying is not, carbon is not present in the gas phase. Right? So no effect of the chemical, but even if it's a heterogeneous reaction, multi-phase, there's none of the phase equilibrium relations come into play. So that we continue to have, this is a very unusual case. Many cases like this discussed in the books, where you don't encounter the phase equilibrium relations to come in. So only the chemical equilibrium criterion that we need. Now to take a slightly more complicated example, again take a somewhat simpler example than the one found in sand. This is somewhat like a mixed reaction absorption system. Just as you have reactive distillation, this may be considered as reactive absorption. And so what Sandler considers is a two-phase system. Right? So, I mean, the details of the calculation are not really part of the course, but at this point, how to approach. So those people who have to deal with, in the future, if you have to deal with multi-reaction, multi-phase, you will get some point as to how to go about doing it, even though I am not covering multiple reactions here. So what he says is this is now a mixture of N2, H2 and NH3. This is the gas phase, and here reaction is taking place. And now point out without getting the complication due to multiple reactions, I will just point out the combined effect of reaction and phase equilibrium, how they appear. You could have simplified the problem from Sandler. So now he says there is also water. So simultaneously you have absorption into water. And the Sandler considers absorption of both nitrogen and hydrogen. If you look at the final answers he gets, that will be a much more complicated problem than the one I'm going to just point out. The values are very low. So for all, it's a good approximation to neglect the absorption of nitrogen and hydrogen in the water. And then I have only NH3, and here he says neglect the reaction of ammonia absorbing in water, and actually gives a reactive absorption also in the sense that you can form ammonium hydroxide. So he says neglect that and consider ammonia to be physically absorbed into water, even though that's not quite the case. Right? So we have now two phases. Reaction is taking place in the gas phase, and we have absorption of the ammonia. So now let's look at what are the equations coming from phase and chemical equilibrium. The equation for chemical equilibrium is very simple. I am going to have to consider only this reaction. So that would be mu 3 2 times minus mu n2 equal to 0. Now it's important again to put the phase, because ammonia is now present in both the phases. So it's important to put when I am writing this, of course, if ammonia is present in this case, it will be equal to the chemical potential of ammonia in the gas state, but it's still important to put this because now I am going to express this in function of YNH2. And so this is also the gas state. This is also the gas state. So one equation, and another equation is ammonia is the only component that I am assuming is present in both the cases. So I have gas. We have now two equations. This is how the combined effect of chemical and reaction equilibrium would have to be taken into account. Of course, as he assumes, nitrogen and hydrogen are also present in both the phases, then we have to have the equality of those chemical potentials also. That will be even more complicated. So I have simplified it so that we just consider the effect of both. Now, again, looking at it from the phase rule, and we will see how the actual calculation that Samuel does is totally removed from the way we approach the phase rule. Typical vapor equilibrium calculation. Now the variables are temperature, pressure. Now I can put YN2 or YH2 and YNH3. And of course I can put XNH3. So 5 variables. Right? Five variables, and then what are the equations? The equations are what we have written down. Right, so what is the degree of freedom? F is equal to 5 minus 2, which is 3. Now let's compare with what the phase rule gives. Right? So what does the phase rule give? F is equal to number of components. Number of components, I will take all the components in the combine both phases. 4 minus 2 phases plus 2, and then minus 1. There's only one independent reaction. Right? And so minus 1 is equal to 3. So it matches perfectly. There's no problem there. But again, when you look at the way he solves the problem, you will see that now what is it that we have to find in this? Right? We have to find finally the composition of both the mixtures at equilibrium. So I have to find not only YNH3 but also XNH3 and YN2. Right? All of them have to be found actually. So what is given would obviously be, now I have to, again, typical reaction equilibrium effect will come in. So what I am given is N2 naught, NH2 naught. So now you see that I am totally introducing a new set of variables. If I have to really solve the problem that is given, so the phase rule analysis doesn't really help me that much. So it's not that I have an independent choice of any temperature, pressure, of course. But I have to choose one or more factors. That's not the way the calculation proceeds. So the calculation to be done properly, I have to start with an entirely different set of variables. N2 naught, NH2 naught, and of course NH3 naught, NH3 naught, and NH2O naught. All have to be specified. Now, what can I say about N2? N2 is entirely due to the reaction, because N2 is present only in the gas phase. You will see now new complications will arise because ammonia being present in both the phases. So we introduce a new variable other than just the reaction extent or the reaction conversion. Right? So if I now introduce, as I did earlier, NN2 to be NN2 naught times 1 minus x. So the conversion is really the conversion associated with nitrogen. We run out of time, so we will continue this. So now the main point is N2 is there, NH2 also we know how to exchange the equation that we had earlier. Now with NH3, right? Also same equation, NH3 naught plus 2x, is it? Whatever, right, to X. But the point is NH3 not alone is not only a combined variable, but actually I need to bring in both N and NH3. Vapor into account. It doesn't, will not give. There we have only one phase, so only vapor phase. So NH3 not plus 2x will give me the total number of moles of NH3 in the mixture. But this also will give, but I also have to find out what NH3 L and G are separately. G. So we'll have now a new variable coming in, right? So that should not. So this is the new. So now there are actually not two variables because the point is now I have to express the mole fraction. So what are the equations? This is now going to give rise to the mole fraction equation. This will give rise to another equation. So there are two equations. The new variables you will see that will come in will be either one of those, right? Because this is equal to NH3 naught. Maybe not. We have to see NH3 naught plus 2x. Because x is a variable. So this is here. This will give an equation connecting the two. So this is NH3 naught plus 2x. Now this is obviously we will have to specify. So we now have on top of x, we have to choose one of these as variables. So the problem will automatically give rise to two variables that you have to determine, right? Because the third variable NH3L, because I have this equation, once I know x and NH3G, I know NH3L. So when you write the whole system of equations, what you will find is that the variables that will come into play are either this and this or this and this, and I have to solve them using the two equations. So the general framework to handle multiple reaction, multiple phase seems to be somewhat elusive. It seems to have gone in many of the books as problem by problem, and you can easily convince yourself what are the variables to be chosen and how many degrees of freedom. I have only two equations here. So whatever variables I additionally introduce, I have to specify all of them except two variables. Right? So that is how and those are not these selected necessarily from these variables. So the combined treatment of reaction phase equilibrium seems to be somewhat in a general framework, seems to be not quite carried out conclusively, but you can certainly do problem by problem and solve it. We will see how to go about solving this problem in the next class and discuss a few other topics.